Hi, my name is Clark Zinzow, and I'm going to be talking to you today about per-epoch shuffling data loaders, and specifically the one that Ray has developed. First, what's this talk about? At a high level, quick overview. We're going to both motivate and talk about the specific challenges of creating a shuffling data loader that can handle large data scales and distributed model training. And we're also going to describe what we feel is a compelling rate-based solution. First, a little bit about me. I'm a software engineer at Anyscale. I've been here for a little bit over 3 months. I've been working on the core array system, focusing on large-scale data processing, and then also doing some work in the integration space, like this shuffling data loader, as well as Dask on Ray. And before Anyscale, I was a Ray user, so I will always fight for the user because I used to be one. So first, what exactly is a shuffling data loader, and why do we need it? A brief overview of your typical ML pipeline. You typically have a data preprocessing stage, a model training stage, and a model deployment stage, with the last also being known as model serving or inference. And what we're interested in this talk, since we're talking about a shuffling data loader for model training, we're interested in this data preprocessing and model training stage interaction. First, to dive in a little bit more into this interaction, typically you store your data in some intermediate storage, such as like S3 or HDFS, and then you load it from that store when you are starting to train your model, and you are going to load it from that store often at the start of every epoch. So what's the big deal? Why do we need like a shuffling data loader or whatever? Like loading data from a store is super simple, right? You just read it. That's it, right? Not so fast, not really. Especially when you start approaching large data scales and coupling that with wanting to do distributed data parallel training, such as essentially to increase like the scale of data that you can handle, where the data maybe can't fit into a single trainer node, or potentially to speed up training by parallelizing it. And also a few things that make this extra tricky. We're not loading the data just once. We're actually loading the data at the start of every single epoch. So if data loading ends up becoming expensive, you're not going to just have to absorb that expense once at the beginning of training. You're going to be hitting that expense at the beginning of every epoch, and it can really slow down your training. So there is like a tiny bit of pseudocode of what usually the loop structure looks like. For every epoch, you're loading your data from the store. We're also not just loading data into a single trainer. We're loading partitions of the input data, partitions of that data in the store, into multiple trainers, often spanning multiple machines once you start getting into distributed data parallel training. And we're also not just loading the data, after all. We're also shuffling the data at the start of every epoch, or this is often desirable, and I'll talk about why that is in a little bit. So typically the data comes through a shuffler. This could often be the shuffler process could be its own service. The shuffler process could be on each of the trainers. It depends on the data loader implementation. And the shuffled input partitions are then sent off to the individual trainers. So a trainer will just operate on a subset of the data. So why do we want to shuffle the data at the start of every epoch? You know, you're used to a model training, you shuffle your data once before starting to train, perhaps in Spark, and then you load it. And you know, you're like, cool, I shuffled my data, I decorrelated the samples. So why do you want to shuffle at the start of every epoch? How does the model training actually benefit? Well, at a high level, shuffling decorrelates samples within and across batches. And this is both true when shuffling data before starting a training run, like doing a single global shuffle to decorrelate all of your samples. And this also stays true when talking about batches across epochs. Specifically for the per-epoch shuffling case, per-epoch shuffling reduces variance, improves generalization, and prevents overfitting. For batch gradient descent, which is obviously very popular, also known as mini-batch gradient descent, and many people just call it stochastic gradient descent nowadays. By shuffling in between epochs, the batches are more representative of the entire data set and fundamentally improves the estimate of the true full data set gradient, which after all is the entire point of batch gradient descent. And this applies for both batch and stochastic gradient descent. The gradient updates on individual samples are independent of the sample ordering. And this can be very, very important. For example, if your samples end up being ordered by time or label, you could have some really nasty hidden correlations that end up making your model overfit to weird esoteric properties of the data set, which isn't great. And this holds as well for every single epoch. You don't want your model getting like overfitting on the ordering of that initial shuffle. You want it to continuously see newly ordered batches sampled from the global data set. And the end result of this is that you achieve better model accuracy after a set number of epochs. So in a given set of epochs. And you could think of it as like per epoch shuffling, improving the statistical gain of each step in the training process. There's a lot more details on why this is the case and why it's nice to shuffle at the start of every epoch. A lot of interesting recent papers also proving also going through the convergence analysis of like stochastic gradient descent, for example. So why is this hard? Like, what are the challenges in creating a shuffling data loader? Can't you just read it all into memory and then use random.shuffle and shuffle a list of data of the list of samples? Well, as I mentioned before, once you start getting to a certain data scale where that becomes infeasible to load it all into memory on a single machine, which is also the motivator for doing distributed data parallel training, or one of the motivators, things get way more difficult and also way more fun. At a high level, your requirements for this shuffling data loader is you want a high quality global shuffle. You want no significant increases in training time, due to the trainers sitting there waiting for the shuffle to complete. You don't want that to happen. And then you want very convenient integration with machine learning frameworks, like nice UX, nice APIs, to integrate with frameworks such as Torch and TensorFlow. So what solutions to this already exist, and how exactly do they fall short? Because we wouldn't be here at this talk if there is currently a solution that was awesome for all use cases. There are a couple of key pitfalls that we've identified in the existing solutions. There are, of course, the framework-specific solutions by PyTorch and TensorFlow. And that ends up being a bit of a con because you have to learn the specific APIs for each of these data loaders, and then you're locked in to that framework. And you often have to juggle like unique performance characteristics for any fancy shuffling that might be going on under the hood and stuff like prefetching. The shuffle is not global, and this is true for PyTorch, TensorFlow, and also Petastorm. Petastorm is a data loader out of Uber, an open source data loader. And although it has a pseudo global shuffle, it only shuffles at the granularity of row groups and files. So it's not fully global, like at sample level granularity. Also, we've heard reports of performance issues from both PyTorch and Petastorm data loader users. Another option is to try and do a global shuffle with an external service that's running on separate infrastructure like Spark, and to try and interleave that with training. Of course, that has the issue of it has to run on separate infrastructure compared to your distributed training infrastructure, which is never fun for people in charge of that ops. Not to mention also the cost, worse resource utilization if those resources can't be shared. And it's also very difficult to integrate with ML frameworks. That's like separate Spark shuffling service. It's a little bit tough to interleave it with training and to do stuff like pipelining, shuffling with training in a nice way. We've heard from a couple of users that this is an issue. One of the biggest users that we've been working with is Uber's deep learning teams. And so they were experiencing a couple of key issues. First, when global shuffling was turned on within Petastorm, they were experiencing latency spikes and throughput instability. And as you can see from this graph over here, The baseline shuffler was synchronous, not doing any pipelining, and the async shuffler was doing pipelining of shuffling with training. And even with the pipelining async shuffler, shuffling data loader, they were still seeing these random, like up to 10-second latency spikes, causing trainer stragglers and slowing down training overall. And then when they tried to mitigate those latency spikes and throughput instability by turning off the global shuffling and just doing per input partition, per trainer partition shuffling, they found that due to the statistical sampling of the training data being degraded by not doing a full global shuffle at the beginning of each epoch, they saw a large training loss oscillation. So ultimately, as you can see here, their training loss oscillated like crazy. And so basically it took them longer to converge to a nice accuracy. And so, yeah, the fundamental result of this is that model accuracy took a big hit. Both of these issues severely affected their model accuracy within a given set time window, and their particular use case was a concrete like 12-hour time window where they wanted to get the model as accurate as possible. And in addition to Uber looking for a solution, even some other users are actually using Ray to build their own data loaders. One example of that is some people at NVIDIA. They were experiencing issues with the PyTorch data loader, particularly around hanging. A little bit of detail in their use case, their models were small and I/O bound, very few model parameters. So data loading performance is very important. It was their most significant training bottleneck. PyTorch's multiprocessing data loader occasionally was hanging, which was hurting their training times. That's no fun. And they built a simple Ray-based data loader, which was basically a drop-in placement for the PyTorch multiprocessing data loader. And they achieved higher throughput than TensorFlow's data loader. And also they matched PyTorch's data loader throughput, but without those occasional hangs. And so this was a very simple, straightforward drop-in replacement, nothing super fancy and Ray specific. And they still were able to meet PyTorch's multiprocessing data loader throughput, despite Ray having more overhead than Python's multiprocessing. So our specific solution, this Ray-based shuffling data loader we've been working on, why exactly is Ray a good fit? Why would you want to use Ray for this? First, great system design. Ray has some awesome system characteristics that I'm going to talk about in a bit. And they also have a large ecosystem around machine learning, around that entire machine learning pipeline. So first, Ray's system design. Three big aspects: the support for heterogeneous resources, the distributed in-memory object store, and really fast, smart, decentralized peer-to-peer scheduling. First, the array cluster can support node types with pretty disparate resources. So for example, it could have different hardware like CPUs and GPUs. It can have a differing number of CPU cores, and each node can have a differing amount of CPU memory. And each of these heterogeneous resources are schedulable at a very granular level, at the task and actor level, which enables fine-grained resource provisioning. And then the distributed in-memory object store, which is Ray's, probably one of Ray's biggest and best features. It has two core dimensions that make Ray awesome. Its optimizations around performance and its assurances of reliability. For performance, particularly for shuffling, intermediate results and shuffled outputs are transparently cached in memory and transferred over the network. Very transparent to the user level API, even in this case, the user being the implementation of the shuffling data loader. We don't have to manually deal with when to transfer data over the network or how to optimize data being cached in memory. That's done by Ray automatically. And then also for reading data that's on the same node, due to the distributed in-memory object store using shared memory, we get zero copy reads, which decreases the read time. Really nice when it's large data. And then as far as reliability goes, the Ray scheduler limits the total memory that can be used by objects in a single node, and this prevents spurious out-of-memory errors, which is great. And then beyond that, if that fails, when the object store ultimately becomes full, objects are spilled to external storage. So essentially, your working data set can exceed the cluster memory, which is really nice. That used to be a hard cap, and we're continuing to work on this too, essentially with the goal of providing like infinite object space that will just smartly cache things in memory and then spill to disk when needed. We're continuing to optimize that all the time, that layer. And then scheduling. As I mentioned, it's a decentralized peer-to-peer scheduling. There's no global scheduler bottleneck. This allows much larger cluster scales and very high throughput because you don't have that central bottleneck. We also have like some things like hot node mitigation, where we'll attempt to schedule tasks on the nodes with low memory utilization. And this prevents, for example, spurious out-of-memory errors, which are never fun. We also have locality-aware scheduling, where we'll try to schedule tasks onto the node with most of the needed task dependencies, most bytes already local to that node. And this minimizes object transfer, which essentially provides like faster task execution, and also minimizes like network saturation and stuff, making the cluster as a whole more reliable. The Ray ecosystem too, big pro of Ray. We have integrations around data preprocessing, model training, model serving, all on a single Ray cluster infrastructure. And so this is a brief little overview. We've got some Ray native libraries for machine learning, such as Tune, RLib, Ray Serve. And then we also have some third-party integrations, including distributed training options, such as Horovod. And it's all running on top of Ray. This is like universal like compute substrate. And then Ray can run on top of your favorite cloud. It could run on Kubernetes, and it can run on-prem. Now, we've finally gotten to the design of the shuffling data loader, the big meat of the talk. So I'm going to talk briefly about the API for the data loader and its architecture. First, if you're familiar with the PyTorch data loaders or with the TensorFlow data loaders, it offers a similar dataset API, particularly an iterable API that yields these globally shuffled GPU batches, hiding all of the shuffler like implementation and all that complexity. That distributed shuffle is hidden underneath a simple iterator API. So here's an example where you configure the shuffling dataset with different parameters, such as like file names pointing to the input data, number of epochs and trainers, your GPU batch size, the rank of the current training worker, and then some shuffling specific little tweak parameters that allows you to tweak the shuffling implementation. And then there you see the usage, where you essentially just iterate through the data set and get back your batches. The dataset will kick off the shuffling in the background as soon as that shuffling dataset is constructed. That's done upon instantiation. And then in the background, it will use the Ray cluster to pipeline shuffling with model training up to the max concurrent epochs throttling limit that you give it. So for example, at most 2 epoch shuffles going on at once. And the training data can be read from local disk, S3 at HDFS. If you check out FS-spec, everything that FS-spec supports, the shuffling data loader will be able to read from. And then specifically for Torch distributed data parallel training, we have a Torch dataset API, which is a very light wrapper around that last dataset. As you can see, most of the construction parameters are the same, except for these feature and label specs. And these are used to transform the GPU batches from the pandas data frames that the base dataset that I just showed operates on to PyTorch tensors, and it transparently does that using the provided feature and label spec. And it'll try to smartly infer that spec as well, and we might add like auto detection based upon introspecting your data to try to auto detect that spec in the future, for example, from the Parquet metadata. And this will seamlessly integrate with Torch training on Horovod on Ray as well. So distributed training all on top of Ray using the Horovod integration. To briefly go over that, Horovod is a distributed deep learning training framework that supports all of your favorite machine learning frameworks, particularly TensorFlow and PyTorch, very popular. And you can actually run Horovod on a Ray cluster. This kind of shows an example API of how to start it up. I won't go into that too much, but within that training function, you can actually use our data set that will run on each training worker and just yield those GPU batches as you would with your normal like torch flow when iterating over a data loader. So the architecture of the shuffling data loader is I think, interesting thing to talk about. First, you have some input data in your store. You partition that data and send it out to some number of mappers. Those mappers will then further partition, or each mapper will partition into your number of reducers, like partitions. So mapper 1 will send num reducer partitions out, so further chunking of the data. And then the reducer is in charge of shuffling that data and then sending that data to a queue, to this global queue. And internally, that global queue will have a couple of local queues that each trainer will pull from individually. And so that's really just the shuffling implementation. And the reducer will do like sample level shuffling, like it'll take all of its mapper partitions and shuffle up those samples. And also this queue is streaming. It just works with references to the data, not the actual data. So the trainers will pull directly from the reducers. The queue is just in charge of queuing up those references and also applying back pressure on the shuffler, which I'll talk about in a bit. We have a couple of key optimizations. We have pipelining, prefetching, and I'll hint at data locality. I'm not going to talk about that in this talk, but we're currently working on co-locating reducers with trainers to minimize data transfer. First, pipelining. What we do is we pipeline data shuffling with your model training. So the shuffling data for future epochs is done concurrently with training for your current epoch. And to briefly illustrate this, let's say we kick off shuffling for epoch 1, and then we can also concurrently kick off shuffling for epoch 2. In this case, you can see these two shuffling lines as like the two slots, because we allow at most 2 concurrent epoch shuffles at once. So those two are kicked off concurrently, and then once the first epoch's worth of data is done being shuffled, we can send it off to a trainer. And then this trainer will say, we don't consider that like shuffled data for that epoch released until that trainer is done with training on the first epoch. So that's what the yellow indicates there. Like we essentially can't start any new shuffles there. That's just an illustration of our throttling on the shuffling. And then once training for epoch 1 is done, we kick off the shuffling for epoch 3. And then we can also immediately kick off the training for epoch 2 because we've concurrently shuffled in advance the data for epoch 2. And then obviously I'm showing here how slot number 2 is blocked until training on epoch 2 is done. And then as soon as training on epoch 2 is done, we can start like another epoch shuffle. We could kick that off, and so on and so forth. So that's essentially how we do pipelining. And the end result is that if the throughput of the shuffler is greater than or equal to the throughput of the training, after the first epoch, all the trainers will always see hot GPU batches after that first epoch. So they should never be sitting there waiting for a shuffle to complete. And then the back pressure on the shuffle is enforced by the queue, adhering to that throttle limit that we mentioned before, and as illustrated in this diagram. In addition to that, we also have prefetching from the queue, where trainers will prefetch the batches of shuffle outputs from the queue. And this pipeline's basically data transfer across nodes with training on the model. And so this is just a small further optimization. So there's an example of synchronous fetching from the queue versus here where we say, give us back, for example, like up to 3 GPU batches at once. And that it's just a smaller little optimization to mitigate the number of times that we're sitting there waiting for data to be transferred across nodes. And so that also is a big help to mitigate stragglers when we're sitting there waiting for data to be transferred. And then if there's a GPU batch available, trainers will always see that as soon as possible. And so we've found in practice that this decreases average and max batch wait time on trainers, which is great. Training goes faster. And then I'll briefly talk about data locality, but I'll go into this more probably in a future talk. We're currently exploring placing shuffle reducers on the same node as trainers, as I mentioned before. And then this should virtually eliminate the communication between reducers and trainers, which is great. Higher throughput, less batch wait time spikes. And so this array-based solution addresses the following pitfalls that we talked about before. It's framework agnostic. The shuffle is truly global. It's a truly global shuffle. It mitigates the performance issues that the PyTorch data loader and Petastorm data loaders have experienced via pipelining, prefetching, and then also raised system characteristics. It runs on a shared ray cluster with your trainers. It's easy to integrate with all of your favorite machine learning frameworks. It's essentially just an iterator API, which is super easy to match any ML framework's dataset API. Brief discussion of some benchmarks. When scaling the cluster, for example, the benchmark config, we're reading this data from S3. Those are the EC2 node types, and then we have 110 gigabytes of object store per node. And as you can see here, when scaling from one node, which is at 4 million records per second throughput, we achieve 5.5 million records per second throughput. And this is not adhering to linear scaling because there's some added overhead when going from one node to 4 nodes. That's all that you're always going to hit. And then also in addition, shuffling is an all-to-all dependency. So shuffling, you're not going to be able to get linear scaling with something like shuffling. So what we're looking at here is we want to see a little bit of uptick in the throughput, ideally, because we have more compute resources available, but we really just don't want to see a degradation in throughput. And then as far as for scaling the dataset size, those last two data points there with 200 million records, this one is with 400 million records, and we see that we still stay around that like 5 million records per second throughput. And we also have some recent optimizations that will probably greatly improve this baseline throughput. This was a rather naive implementation from earlier. User stories. So how happy is Uber with this, for example, whose user we're working with closely? Uber is currently experimenting with integrating this shuffling data loader into their deep learning pipelines. And at their current data scale, we are able to consistently deliver these statistically great globally shuffled GPU batches to their trainers in 100 milliseconds after the first epoch. So the trainers really never have to wait at all. The key takeaways from this talk. Per epoch shuffling is needed to avoid overfitting from many deep learning workloads, as we talked about earlier. Ray has a compelling data loader that seamlessly integrates with torch training on Horvath on Ray. And Ray, as a common substrate for your machine learning pipeline, gives you best-in-class UX, performance, and ops. If you want, please connect with us. I have some links here. The slides will be shared. You can check out the data loader repo. You can come talk to us on the Ray discussion forum. And also, as always, we're hiring. So if any of these problems are interesting to you, please come talk with us. Thank you and enjoy the rest of the summit.